So let's turn our attention to the conformation of the molecules, their spatial orientation, and think about the strain energy that can sometimes be seen from certain conformations. So let's start with ethane, one of our simplest alkanes. And of course that carbon to carbon bond has completely free rotation through the bond through 360 degrees. Now, although we should have free rotation, there are some conformations which are preferred and some conformations of the molecule which are actually avoided because they have strain energy associated with them. Now, to see what's going on, we need to look at a Newman projection, which is to look down the carbon-to-carbon bond and look at the groups which are attached and their spatial conformation around the carbons. So it breaks down into two basic conformations. And the first one we want to think about is this staggered conformation. So for every CH bond on the front carbon, there's a CH bond on the second carbon behind, which is rotated at an angle of 60 degrees as we look at it. Notice that the hydrogens attached to the carbon in the front, their chemical bond line goes all the way to the center of the circle, the red, purple and grey, the red, purple and grey, and then the CH bonds on the carbon at the back eclipse behind the first carbon. Those bonds only go to the edge of the circle as far as we would be expected to be able to see them. So the black, orange and blue, the black, orange and blue hydrogens on the carbon at the back, because we're looking from left to right down this carbon to carbon bond. So with this 60 degrees angle from each CH bond to the next, this is what we call the staggered conformation. Now the alternative conformation that we see and use quite a lot is what we call the eclipse conformation. So there's been a slight rotation through the carbon to carbon bond here, and it's now putting each CH bond on top of one of the CH bonds on the second carbon at the back of that carbon to carbon bond. Now I've rotated it slightly, skewed it slightly, so you can get a clearer picture of the bonds in front on the first carbon and the bonds at the back on the second carbon. But it's basically an eclipse conformation. And these are the two views that we're going to use and compare and calculate the strain energies for. So let's look at the strain energies we see for ethane with these two conformations if we draw them out again. Now for that staggered conformation, it maximizes distance between the chemical bonds and the atoms. So the staggered conformation for ethane has zero strain energy. However, the slight rotation through the carbon to carbon bond, putting the carbon to hydrogen bonds in this eclipsed conformation, starts to show up some strain energy. And for ethane in the eclipse conformation, we see 12 kilojoules per mole of strain energy. Now the source of this strain must be the eclipsing of these CH bonds behind each other, and with 1, 2, 3 of them, that 12 kilojoules per mole of strain energy must be divided between all 3 of these CH eclipsings. So it gives us a first kind of strain. When a CH bond is eclipsed in front of another CH bond on the next carbon, it leads to 4 kilojoules of strain energy each time. So it gives us a total of 4, 8, 12 in total as we look at this eclipse conformation. So that's for our first kind of strain energy for this problem. And it's because we have bonding electrons from one CH bond getting too close for comfort to the bonding electrons in the second CH bond on the second carbon. And this strain energy is what we sometimes refer to as torsional strain, because for the carbon to carbon bond to twist into this conformation, it's causing this kind of strain energy. So as we rotate or twist the carbon-to-carbon bond into that eclipse conformation, putting hydrogens on top of each other across the carbon-to-carbon bond, it leads to this 4 kilojoules per mole of strain energy. Let's look at another example. Let's look at propane. And again, we'll look at the two main conformations, the two extremes, a staggered conformation and an eclipse conformation, and look at the strain energy we'd associate with these molecules. Again, with the staggered conformation, as we rotate the bonds to keep these CH bonds and methyl groups as far away from each other as possible, that's the low energy form, and we have zero energy, zero strain energy associated with the staggered conformation. Incidentally, our Newman projection here is specifically coming from looking through this carbon-to-carbon bond through carbon 1 and 2. So in the front we've got the red, grey and purple hydrogens of carbon number 1, and then at the back on the second carbon, eclipse behind the first one, we've got the black and the orange hydrogens together with this blue methyl group. So no strain energy associated with the staggered conformation again. But when we look at this eclipse conformation, by rotating this carbon-to-carbon bond a little bit, and we put these groups on top of each other, we now see 14 kilojoules per mole of strain energy. That's more than we had for the last example with ethane. Now we know this hydrogen to hydrogen eclipsing through the CH bonds leads to strain energy, 4 kilojoules per mole each time. So the additional strain energy must be because of this hydrogen to methyl group interaction. To get it up to a new total of 14, that strain energy now must be 6 kilojoules per mole. We've got a bulkier group in the methyl group, and it leads to more strain energy in this eclipse conformation. So this is our new and second kind of strain energy, which is still mainly torsional strain, because the molecule would be strained if it rotates and twists into that eclipse conformation. So 4 kilojoules per mole when we put hydrogens on top of each other through the CH bonds, and 6 kilojoules per mole when we put the hydrogen on top of the methyl group. If we look at butane and look at our Newman projection through the carbon 2 to carbon 3 bond specifically, and look at the groups attached, again looking at the staggered and the eclipse conformations. But first let's just look at the staggered conformations, because we get different forms of them. The first one with the methyl group on the front and the methyl group on the back on opposite sides of the plane of the carbon 2 to carbon 3 bond, and we have zero strain energy in this conformation. However, if we were to rotate the methyl group on the first carbon, rotate it 120 degrees, so the methyl group would now be there, and the purple hydrogen would now be here, and the red hydrogen would now be at the top. If we rotate through that carbon 2 to carbon 3 bond to give this new conformation, which is still staggered, we start to see some strain energy, 3.8 kilojoules per mole. And if we rotate this methyl group again 120 degrees and move each group on the first carbon around clockwise, for this new conformation, we again see strain energy of 3.8 kilojoules per mole. And that strain energy, which wasn't there before, must be because of these adjacent methyl groups, which are only separated by 60 degrees as we look at it from the Newman projection perspective. So we've now got strain energy in the staggered conformation that we didn't have before. A methyl group 60 degrees from another methyl group gives 3.8 kilojoules per mole of strain energy. So this is our third kind of strain. We had the 4 kilojoules and the 6 kilojoules for hydrogens to hydrogens and hydrogens to methyls, but that was in the eclipse conformation. This new strain is different from the others because we're seeing it in the staggered conformation, and it's what we sometimes refer to as a gauche strain. This is mostly steric strain, which is different from torsional strain because we've got atoms which are encroaching on the radius of other atoms. Basically, atoms are trying to occupy the same area of space at the same time. They're stepping on each other's toes, effectively. Now if we looked at the eclipse conformations for the butane, and of course we're getting strain energy in this molecule, as we would predict, because of the hydrogen to hydrogen overlap. But the total strain energy in this molecule is now 19 kilojoules per mole, more than we've seen previously. We know about that 4 kilojoules from the hydrogen to hydrogen, so this additional strain to give us a total of 19 must be because of this methyl to methyl interaction, which must be 11 kilojoules per mole of strain energy. And that gives us our fourth and last kind of strain energy for this video. So we've got hydrogen to hydrogen, which is 4 kilojoules, hydrogen to methyl, which is 6, and then almost double, methyl to methyl, which is 11 kilojoules. These are our 3 examples of strain energy when it's in the eclipse conformation. And that methyl to methyl is actually a mixture of torsional, because the carbon to carbon bond finds it difficult to twist into this conformation, but there's also steric strain because the atoms are physically entering each other's radius, sitting on top of each other. Our last kind of strain, the methyl to methyl, is different from the other 3 because we're getting this strain in the staggered conformation, not the eclipse conformation. So most of our strain energy comes from the eclipsed, which is mostly about torsional, with bonding electrons repelling bonding electrons. And our last extra strain is this one with the staggered conformation, which we call a gauche strain. And it's methyl groups too close to other methyl groups, separated by that 60 degrees. So one last look. With the staggered conformation, it's just a gauche strain, which is 3.8 kilojoules. Remember, it's got to be methyl groups which are just separated by 60 degrees. Methyl groups separated by 120 or more would not cause this gauche strain. And our other strains are all about the eclipse conformation, 4 kilojoules per mole for hydrogens on top of each other, 6 kilojoules for a hydrogen and a methyl group on top of each other, and 11 kilojoules per mole for a methyl group on top of another methyl group.